The universe is calling me. It speaks both day and night. It's full of dark and light, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's home. Boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Hello, welcome everybody. How you doing? It is me, Mark D'Antonio, here with you guys on the SkyTour's live stream for this beautiful July 27th of 2024. We are currently sitting here in the constellation, not of Cygnus Ray, so lucky you, but we're in Scorpius. And we're going to be poking around at some of the beautiful things in Scorpius that are here. Really neat stuff. Daryl is having issues with his computer tonight, so he may or may not join us, but we're trying. And let me actually bring up my volume. Sorry about that. Is this a little better? I think this is better. And I apologize for that. I want to say hello to everybody who's here earlier. Looks like we have Tim F. was the first one here. Cosmic Ray, Carl Becker, nice to see you. And Mr. Django, that's Steven in Belgium. And we have Donald Kunzer's with us, Claudio Ramos from Chile, where it's chilly, just as he commented before. C&D Boy from Canada, where it's probably not as chilly. Julian is with us. Hey man, how you doing? Nice to see you. JSCO77, one of our previous winners of equipment. And we will be getting back to doing giveaways, by the way, just so you guys know. And Mindfork, that's Chris. How you doing, Chris? Nice to see you here as well. Alice Pooper is with us. Michael Hedrick is here. Nice to see you as well. And Daryl's going to be here in a minute, and I'm going to give it a shot now to see if I can grab him. So we'll find out right now. We'll give him a ringy ding and see if we can pull him in. So I believe that I am connected to him. Okay, let me do the housekeeping here to get you on real time with me. And here we are, and here we are. And, oh, well, that sounds like fireworks at your end. Okay, nobody can hear you yet, but I'm now going to bring you in. So, welcome, Daryl. How are you?
Well, I'm good. Sorry, I don't know what the heck's going on here. Yes, that was fireworks you just heard.
Yep. Okay. Well, it's good. I saw him in the chat, and I realized we tried twice already to get in here together, and it didn't work. So now it's in. Now we're in. Tonight's a great night. Last night I actually opened the observatory privately just to do a couple of images, and I was blown away by the quality of the sky and the images that we got. It was really, really something. So I was very, very happy to see that. So we're going to try and do the same thing again tonight. So that said, I am going to now show us again where we are. We are currently in Scorpius. Here is Antares, and we're to the upper right of Antares. We're right here by this location, but we're going to go here first of all. This is called the Blue Horsehead Nebula, and we're going to head there right now. It's a really cool nebula. It's a reflection nebula. It's blue, and I think it's dark enough to show. There's the streaks of the stars, and these two stars are usually there when we look at the Blue Horsehead. And if we go to our planetarium here, we jump in here and look at the Blue Horsehead location, all right, we'll see those two stars, and they are right. Let me just bring us where we are here. Okay, so that star we're looking at is Jabba. All right, and Jabba is, I believe, a double-ish looking star, and we're gonna try to more fireworks.
Oh yeah.
Okay, no worries.
I closed the door. Hopefully that'll cut it down a little bit.
Maybe. Okay, so we're going to be focused on this part of the nebula right now and see how it goes. Now, I'm going to set the gain. Now, for those that haven't seen this before, it's kind of important to know that this side of the screen is where our telescope parameters are. But this field here, exposure, and this field here, gain, are the two most important ones. All right, this is our telescope control section here. And this is our telescope and our telescope computer, and you can see what it's doing. Those numbers say it's guiding. And then this right here, well, that's yours truly. And sometimes I will detach from the screen and come over and point things out in the sky for you so you can see, like, this is Java, okay? And do some stuff like that to kind of show you what's going on. And there'll be a screen down here at the bottom that you'll see as well from time to time. And that'll be our stack screen where we're actually dynamically stacking our images. So without further ado, let's do this. Let's go and jump up to a, let's say, 25-second shot. And we're going to go to 250 gain. Okay, actually, I should have done it this other way. Okay, I'll do it this way. All right, so we're up by 50. So our sky is going to be, our noise will be a little bit higher digitally, but we can get rid of that right? So this is what we're looking at here, and the blue Horsehead Nebula is right here, and we should see it. So we're already going. I'm gonna hit the live stack button, and this is gonna bring in our first stack image, and I'm going to get rid of this here. Let's see if our filter was set right. Okay, it's up at 9.5, so we might be getting some wind right now, but we'll keep going. I'll set this to just about 7 or so.
I looked on weather radar before the stream, and it looked like you might have had some storms to the south of Phoenix, possibly working up your way.
Yeah, I don't think those are heading our way. It looks like they're curling to the northeast.
Oh, good.
But let's keep an eye on them. Okay, we're dropping down the error now. Let's make sure. Let's make sure what we got here. As we talked about before, we're looking at, okay, we're getting some wind clearly. We're going to get a weather station out there so we can see the instantaneous wind. Right now, we don't have that. It is, as you can see here, 33, 34 degrees Celsius in the building right now. You can see from that particular field right there. That's in our focuser.
How many degrees in freedom units is that?
In freedom units?
Yeah.
Geez, you'll have to tell me.
How many degrees C did you say?
34.
I'm too lazy to do it in my head. Give me just a second, I'll find out.
Well, you're saying freedom units. I don't know what freedom units are.
Fahrenheit.
Oh, Fahrenheit. Okay, well, that's going to be...
34 C, you said?
Yeah, so we're talking about 90 degrees, I'm going to guess.
93.2.
Yeah. Now, the building's been open for about an hour, guys. I opened it a long time ago. And I there we go. We got our first green. There we are. Okay. So, the blue Horsehead, you can already see this blue haze here. But for us to see that better, I'm going to add some enhancements. I'm going to do what's called remove the color noise. So if you watch the screen right here now, you'll see an instantaneously better shot. Ready? Watch this. Okay, here, watch. Okay, that wasn't as dramatic as I'd hoped. But I think that's because I didn't set the histogram correctly yet. I'm going to color correct first of all. Line up our red, green, and blue fields, and I've done that. And then I will move the mid-level down. It's going to make it look dimmer. And then I'm going to move this one closer to the peak of the curve, which will enhance what we see here. And you can see that the blue now is showing a little better. I can probably bring that in a little bit. All right, if we bring that in, you'll see it a little better. All right, let me get to it. There we go.
Cosmic ray. Celestron just released their new Origin telescope yesterday, a day or two ago.
Now the C-Star competitor.
Yes. It is a fully smart telescope. It comes with a 6-inch f2.2 RASA tube assembly. That's a Rho Ophiuchi Schmidt astrograph. It's got every bell and whistle you could think of. Comes with the camera and the mount, the drive, the electronics, the brain, everything to do what your C-Star does. They finally did it, and I bet it's just the first of many. Mark and I have already talked about this. $3,999 is all it costs.
Yeah, C-Star is $500.
Yeah, I know.
But you know what? You get what you pay for, you know. The C-Star is great if people want to go and just check out some cool things and not have to think too much about it, all right? But if I was to get a telescope, I would want to be able to have something that can peer past a dawes limit that's really, really high. You know, I want a lower number for my dawes limit. I want to be able to see closely separated objects. I want to be able to see spindles of dark nebula. I want to be able to see some incredible tendrils within, say, the Veil Nebula in Cygnus Ray. And those tendrils might not be as visible if that you don't have the resolution to show them. So I'm really a fan of aperture and getting some really good settings in cameras to be perfectly tuned. This camera we have on here is tuned to this telescope. It means that it is set up so that we have the best arc seconds per pixel of the camera sensor, arc seconds per pixel size, such that a ratio such that we can get the best possible resolution out of that camera for the optics we have here. And it's really something. It's made an amazing difference.
Well, I'm torn about this. I mean, I wouldn't need or want a scope like the Celestron Origin, but any Tom, Dick, and Harry with the money, he can do what we're doing right here, right now. The thing actually makes pretty good images for a 6-inch Schmidt reflector.
Yeah.
I'm old school. I learned the sky the hard way by hand. And, nowadays, I see the day coming when people like you and me are no longer needed.
Well, but that assumes we're going to be using the same equipment. That's not going to be true. We're going to be at the next level.
Yeah.
And I'm happy. There we go. Now we can see it. Yeah, I'm happy to do that. I don't have a problem with technology maturing. No way. I'm happy for it to mature. I'm happy for it to get to the point where we're forced to upgrade everything we've got in order to make the next level. I will say this. I know for a fact that at some point, universities, and it'll start with universities and other science organizations, will actually have the ability to put satellites in orbit themselves. Okay, universities especially. They're doing it now with CubeSats. All right, but it's going to be even more than that. They're going to actually have their own telescopes in orbit to look at things. Universities will. I imagine Arizona ASU, Arizona State University, will do it. Okay, I imagine that Cornell will do it. And they're going to end up being able to offer satellite astronomy programs that allow researchers to do real solid research that they've never been able to do before without just getting data from other telescopes. And that's cheaper for sure. However, there's something to be said for having control over your own space telescope. And I can tell you, when that starts to happen, I'll be there. One way or another, I'm going to be there.
Universities will have observatories on the far side of the moon one of these days.
Yeah, I'm sure it will. However, far side of the moon's not too advantageous, actually. Orbit is far more advantageous than the moon. You could baffle off the moon, and up there, all you have to do is be a hundredth of a degree off the lunar surface with your view, and you have a gorgeous view. You don't have the issues with you don't have the issues of the atmosphere, making the entire sky glow on you. Now you might have some secondary reflections from being near the moon. I get it, but it's possible that it may not. It's possible that it may be even better than that. Hi, Eliza. Eliza's with us. Hey, Eliza Raquel, what's happening? Jeremy B, what's going on, brother?
Arthur C. Clarke said we'd have observatories on the far side of the moon, so there.
Yeah, he did. At the time, getting to the moon.
Here.
Izabela, hey, I'm glad she's here. Everybody show your love for Izabela. She's been upgrading our app with all of our latest findings and stuff and working on it. We're still in the process of trying to get it deployed. I've contacted the company and they basically they're not as responsive as we had hoped. So we're not hearing back from them about our app and deploying it. So I'm going to just do what I can to make that happen again. I think tomorrow I'll start writing them a letter or an email to suggest we really want to do this soon. You know. Okay, so we're not getting too many more here. So we're getting some wind out there.
I can sort of see the Horsehead a little bit.
Yeah,
his nose is to the upper right.
I'm raising this up a little bit to start getting more than 4 frames. Yeah, let me zoom out here so we can actually see it a little better. So you can see it there. Here's the more dull brownish cloud, and here's the blue reflection. All right. It's actually dark enough, though. I was doing a 25-second exposure to see if we're going to get interference from sunset light, and we are not. So this is good. Hey, OG, what's going on? OG asked about NGC 4676 in Coma. Colliding galaxies. Can we see that or only Hubble? Saw a video yesterday or today that said the Milky Way and Andromeda galaxy are starting to merge. Well, yeah, the galaxies are pretty big, so we might actually. Andromeda is quite far away, but it's not going to wait till it gets here before we start to get gravitational perturbations from the Andromeda galaxy. So there may be a possibility that we're going to see them early.
Windy.com says you have 12-knot winds.
Yeah, that's what it looks like in here. Something along that line. Let's see what else data is hiding here. Let's push that. Oh yeah, there it is. You can see it really clearly now. Yeah. Okay, well we'll let's see. Let's see if we can use this. Yeah. We're gonna get rid of this. This is really a real strong push, and we don't want to do that, but we can get some of the data here. Let's color correct again. All right, there we go. Oh yeah, color correction brought out the blue nicely. Let's see where it wants to be. That's what I thought. That pulls that in. Let's pull this dark level up our peak a little bit more, halfway to the top. There we go. All right, now we'll just write this in here. This is the blue Horsehead. There we are. All right, and now that I raised our full width half maximum value, we're getting more of the greens, but the wind is still giving us trouble. But you can see that the wind would have ruined our shot. So by being patient, we actually will get our shot. So move this over. There we go. Jerry B says, if I could live at a certain time, I'd be seeing the Andromeda galaxy coming closer to us. It would be seeing, okay, yeah, it would be seeing it coming closer. That'd be one heck of a sight to see. Well, it's possible that you wouldn't see much different than you see now. You might see a second Milky Way in the sky, 2 crossing Milky Ways perhaps, or maybe you wouldn't even see any galactic structure at all, because the Andromeda galaxy might be warping our disk, because Andromeda galaxy has over 1 trillion stars in it, and we only have about 150 billion, maybe 400 billion at the higher count. That's the uncertainty. Within our own forest, we can't see all our trees. However, I will say that when we look at our galaxy, we're going to be, we're going to be intact for some time to come. We're not going to be getting ripped asunder but until the Andromeda galaxy gets here. But once it does, doesn't mean the end. Okay, we're a star, and we're going to have planets around us. What it might mean is that if we are already spacefaring interstellar, it might mean that we might, over long periods of time, have to go either longer or shorter distances to get to our neighboring stars. But understand that every time a star comes near us, it stands a chance of damaging the frail development on the Earth and life-bearing planets. So that's something to be concerned with too. So, but I don't think that we might not even notice the Andromeda galaxy pass through us, other than the gravitational ripping of the spiral arms apart and stuff. We wouldn't notice it here on Earth. It might not even affect us. So we'll have to wait and see. But that's about 3 billion years.
You're no fun.
I know, right? Let's have it now. Okay, we're starting to get good counts now on our full width half maximum. Looks like we're kind of past our windy phase here. All right. So we're going to go up to 15, and then we'll call it for this one and move on.
Looks like one of your observatory images is missing.
What are you talking about?
Over on the left. The telescope views.
Oh, yes. The one that's normally here, it failed to connect, but that's okay. As long as I get this one, which I've always used, I'm good. The second one was just a nice to have. We're working on getting a pan and tilt camera in there, though, so we can just move around, zoom in, and look around at anything at any time. Just like we used to have here, but here it was a Wi-Fi camera, but I don't have Wi-Fi out in the middle of the desert. E-Man, how's it going? Where were you at the star party? E-Man says he just got back from the star party. Okay. Okay, we'll save that. Save it exactly as seen. And let's try seeing what the annotation might give us for this. We can actually annotate what we see. It'll probably identify this star, and it'll identify this nebula, but it might be too big for this view. But we'll see. Yeah, there it is. So this is IC 4592. That's what it shows there. And then this is Hipparchus 79374, known as Jabba. That's V Scorpi. Okay. Yeah, I like being able to identify stuff. We'll save the image with the annotations anyway. There we go. Okay. So now what we'll do is we'll leave this object. We'll pull out more data for you as we go here. And now I'm going to do get us down to our low light view. This is the typical view that we use in order to find stuff, the low light view. Here we are. We'll zoom in. Okay. Okay. Now, from Java, okay, here, this cross shows that. This red box, it moves around, but when it's centered on our view, it's the size of our field, and you can see it written there. Our field is 1 degree, 29.25 arc minutes across. In other words, 1.5 degrees, and the height is 59 minutes, or otherwise known as almost a degree. So it's 1.5 degrees, okay, which is 3 full moons across and 2 full moons tall. Okay, that's what we see. Right, that's what the square is. So whenever we're at something, we will consult this red square to see what we should be seeing within our view. It's pretty cool. All right, now we're going to come down here. We're going to go to an object that I know Daryl really likes. It's called the Rho Ophiuchi Nebula. And then we'll drop down below and check out IC 4603 after that. Okay. There comes our telescope. There's Rho Ophiuchi right here. And there's a brilliantly beautiful nebula right surrounding it, and we'll see. And it's actually much easier to see. And for those wondering, the light we see in here, this is infrared, so we don't. There's not going to be anything to impair our vision in here. We're going to have no problem being able to see in the telescope because of the infrared light in there. All right, it's not going directly into the tube. All right, so let's go back to our amazing view, which is our planetarium view, which allows us to see all this. So we're going to zoom in now on Rho Ophiuchi, and there is a nebula here that we want to see, and that is kind of okay, actually. I'm going to just move us a little bit to the west. A little bit to the west. That's good. And a little bit to the south. There we go. All right. That looks like it should be good. Come back down a tad. And now what we're going to do is we're going to image this section of the sky. Now this is what it looks like. Looks like nothing much happening there. All right. But as you'll see, you're going to actually see there's a dark nebula right here, and there's a beautiful wispy blue structure around this star, around these parastars here. And I'm going to show them to you, and I'm going to go with a 25-second exposure. All right, and we'll start it. You can see our numbers showing up here. That means we're guiding. All right, so off we go, and we'll stack. Live stack. Let's get out of low light mode and go into deep sky mode. Okay, we're now in deep sky mode. So guys, if you like this, please give us a thumbs up. Help us with that algorithm. We're trying to, make our way here. We are a non-profit organization, so we have a new website. Although it looks similar to the old, the new website has all kinds of capabilities and functionality in it. Let's make sure this is. What happened there? Let's wait.
New website.
Yeah. SkyTourLive.org is got a new website. We have 3 rejected here, and I'm wondering why. Okay, it's doing some weird stuff here. I don't know why it's rejecting these. Let's go back to alignment. start again. Not sure why it did that. Let me look. We don't have clouds, do we? We got some light cloud cover. How about that? We're looking. Okay, if you look right down here, let me bring up the constellations. Okay. I know that looks confusing. But we're in Ophiuchi. Down here. Okay, down here is. Let me get rid of these constellations. Okay, we're kind of down here right now, and we have some light clouds, and I'm wondering if this is affecting our ability to guide and capture. That wouldn't be good. Let's find out. Yeah, it's rejecting them. Why? Well, let's try this. Let's try just a 15-second shot as a test and see if this is a strange problem that we're dealing with here. You should be able to guide. Okay, let's just stack it again. Why is it rejecting? Alright, let's turn it off entirely.
Michael H. says, wait. I don't understand that. Are we expecting aurora activity July 27th?
I'm not sure about that. I looked at the auroral oval yesterday, and it wasn't doing anything spectacular.
There was a huge, they called it a halo.
Yeah.
Coronal mass ejection on the sun.
Yeah.
It was came from a Mag X14 solar flare, but it was on the far side of the sun.
Yeah, so it wouldn't
and
hit us.
There was some debate if anything was actually going to come our way.
Yeah.
There was another one a few days before that, and they predicted great things, and it was a total dud here.
That's right.
But it too was on the far side of the sun.
Mm-hmm. I have to.
Michael says because your screen said that a moment ago.
Oh, he's talking about this guy up at the top, unsettled and active. 27th is quiet, 28th unsettled, 29 active. It's possible, but generally, when I've seen things like that, we haven't had much happen, to be fair. All right, let me. I can see what's happening. Look at these numbers. They're so high and so out of whack. I think we're getting hit by some significant wind out there right now. So here's this dashed line is what we normally would have as a limit. But we're way above the limit and the stars aren't elongated yet, which is good. So we'll try to capture with this and see what we get.
OG Skywatch, meaning if the flares and the CMEs don't hit Earth, there won't be any aurora, so I would call that a dud.
Yeah, if they're not coming at us, you know, it's gonna be like directly toward the Earth, which is not actually that common. Hey, Sam S. He's asking us, can we see the Terzan 5 Globular Cluster? Where is that? Do you have any idea, Daryl?
No, I don't. He retracted the message.
Oh, he did? I'm seeing it right now on my screen.
It's gone on mine.
Huh. It's the last message in the list.
Oh, okay. I see it again now. I'd have to look it up.
Okay.
There are tons of nice globular clusters in the part of the sky we're at right now we can look at.
Yeah, there's one right near us right now.
Yep. M4 and others.
Yeah.
Let me look up Terzan 5.
Our numbers are really exorbitantly high, so yeah. I'm not sure why it's doing that, but if I increase this to crazy heights.
Terzan 5 is a heavily obscured globular cluster belonging to the bulge central star concentration of the Milky Way galaxy. It is one of 6 globulars discovered by French astronomer Agop Terzan in 1968. If it's heavily obscured, we're probably not going to be able to see it.
Maybe.
It's in Sagittarius in the direction of the Milky Way center.
Yeah. Well, as the time goes on here, we might be able to see it. Because currently, if we look at our system here, we back out. We're to the right of the meridian with everything we're looking at now. And we'll check out another cloud just below here, IC 4603, in just a minute. And we have, on the meridian, we have the Milky Way. And we should be able to see Terzan 5. What's the RA and deck for it?
I closed the window already.
Okay. Well, let's see if it shows up in the...
I mean, it says heavily obscured.
Oh, it's okay. Let's see if...
Give me a second.
It doesn't show up by that name. That's okay. Okay, so let's come back here now.
I have the coordinates if you want them still.
Yeah, what's it? RN deck?
Yes.
Yeah. Just tell me what they are, but to hang on to them. I won't be putting them in yet. I'm going to go to M4 first. I'm sorry. I'm going to go to this IC, then M4. Then we can try Terzan if we have time. What's the RN deck for it, though?
Right ascension is 17 hours, 48 minutes, 5 seconds.
Okay.
Declination is minus 24 degrees, 46 minutes, 48 seconds.
All right, well, we're minus 23 right now. And an hour later, so it might be visible to us. It's going to be right down near Sagittarius A, I think.
I said that earlier. It's
Oh, you did? I'm sorry.
yes.
Michael Hedrick, did you ever figure out what the mystery lights were in Arizona? I did not, Michael. That's a true mystery, actually. I could not figure out what that was that we saw on that all-sky cam. And E-Man says, Mark, can we take a look at the double star system? That's in Lyra, Epsilon Lyra. We can, but let me explain. This telescope has a wide field. As I mentioned before, 3 full moons across and 2 full moons tall. Okay. Here comes a satellite through our view. Let me save it before that gets polluted further. Oops, I'm saving it in the wrong spot. I'm just going to let it go. Now I'll change the name. Rho Ophiuchi Nebula. Then it'll ask me if I want to change things. Yes. Okay. Now we'll save it again. And save it again. I'll fix that when we get online. So you can clearly see this beautiful nebula here. You see this dark cloud here. I'll try to bring that out a little bit more now. And the way, yeah, I know. No, let me fix that. I don't know why it said it couldn't do that.
Hey man, the end result of what Mark was saying, this is a low power wide field instrument. He could point it at Epsilon Lyra, the double, and we might see the double, but we probably wouldn't see the double. That is, the telescope's focal length is not sufficient to split each of the two stars in the double into the doubles. If Mark is willing, we can certainly take a look at it, though.
Yeah, we could. Oops, sorry about this. Sorry about that. Yes, no problem.
We haven't streamed in a while. You feeling rusty?
No, not at all. It's just that I was trying to change the name there, and I got some error boxes, but I've corrected it.
Well, I'm feeling rusty.
Well, try some WD-40.
I hate WD-40. That stuff is useless. It's worse than useless. Industrial mechanic of over 40 years experience, folks. I refuse to use WD-40 on anything. It's a terrible excuse for a lubricant. And it gums stuff up.
Well, I use lithium grease.
I use whatever's called for in the job.
Hey, Jessica S., how are you? Alright. So, here is the Rho Ophiuchi Nebula, and let me actually try to pull a little more data out of it. So there's a lot buried in here, as you can see. Sometimes you can see that by making a negative of the image. So you can see the dark lanes here when we make the negative here. In astronomy, many times when we were looking at star charts for doing university projects or whatever, we would actually use the negative frames rather than the actual black and white imagery, proper colors, because it was much more visible on the inverted in the inverse. So if I go and do it again here, okay, look at where's the dark nebula? It's really hard to see here. Okay, but if I actually increase this contrast rapidly, and then I do the inverse, this dark lane shows up quite prominently. Look at that. You can see it quite easily now. So the point there is that we would actually take these contrast enhanced images, invert them, and that would give us plenty of data to play with. Okay, so we got 42 of these. We're going to save this. Okay, and save exactly as seen. Yeah. Alright. Alright. So we'll come out of this now, and we're going to go back into low light mode. Alright, and low light mode is like a night vision finder scope, effectively, because we can actually see, kind of peer into the dark a little bit. Alright, now, next what we'll do is we're going to go back to our planetarium program here. And now, from our position here with the Rho Ophiuchi Nebula, which we're going to go right back to here in our program. I want to take us down a little bit south. And so we're here. I'm going to take us down to here, which is just south of it, which is really kind of cool because there's another nebula here that's really fascinating, and they will almost connect to each other. So let's do that. And this one is brighter. It's actually got a lot of dust that's just illuminated, and it's not scattering starlight. And so we will see not just a blue reflection nebula, but we'll see a visible light dust reflections. Okay, and you can even almost see them here now. And what I'll do is I'm gonna center on that, zoom in, and check that out. See, so this is a brighter segment and it's more compact. So we're gonna move this segment here a little bit toward the top of the screen. All right, here we go. And we're gonna move it a little bit to the left. Blues Traveler, how you doing? Memorex. Ron is with us. Ronald. Nice to see you here, Ronald. Thank you, Daryl, for putting that up.
Yeah.
Okay.
Izabela said, "Are you making a mosaic?"
I'm trying to get it just enough of an overlap so we can do that. But I want to catch this whole nebula and not break it apart. So I'll try to do a mosaic with this, because it is close.
Funny, Rho Ophiuchi showed up about a half a dozen times on your server.
Using the application to search for it?
No.
Oh.
On the server.
Oh, sorry. Yeah, I actually I corrected the file names when it was trying to keep sending it up. I'll go correct it later. It's only should have one directory. Okay, let's go into our stack here. And let's get rid of our low light mode. We're going to go into deep sky mode now. And let's see if we capture the first one. Oh yeah, look at that. Beautiful. And let me drop this down just a bit. See if it still works.
Believe it or not, we're about to lose Scorpius already.
I know.
Scorpius is the southernmost of the zodiacal constellations, and it's already declining, I believe. It's going to be dropping in the southwest before you know it.
Okay. This should be good. All right, so now you can see now this beautiful cloud materializing. This is just incredible. I haven't even color corrected yet, so I'm going to hit the color correction now. And then I'm going to drag up this curve. We don't want to go past the curve, but this will make this dust show. This is very small particles of dust, micron-sized dust particles. And it's made of the debris from billions, literally billions, of supernovae that occurred over the previous billions of years in our galaxy. Now, many of these stars are so massive and big, they only live, a few tens of millions of years, because they burn through their hydrogen and they go through the rest of the stages of their life cycle, okay, very, very quickly. And that would take them out of the universe in a very, very short time, only over after a few tens of millions of years. And when they go supernova, they litter the universe with dust that was formed in their outer atmospheres when they were big red giants and supergiants. And that's what we're seeing here. We're seeing dust particles here. This is all dust, remnants of previous stars' existences. I actually have a song that I wrote the lyrics for, and then I have the music and I had it sung by an AI system, and it's about life beginning in the dark. And I'm thinking I might start to play some of these songs at the beginning of our streams. I'm sorry you find that funny.
I'm sorry you find that it's sorry, or whatever you said.
Right.
AI is the devil.
Okay. Well, when you're writing the lyrics and they're not, and all they're doing is putting, and I tell it which instruments to use too.
Blues Traveler has a question for you.
Okay. I asked once what the temperature of an oxygen cloud. You said space has no temperature. That's correct. I lost many nights sleep trying to comprehend this concept. Oh, I'm sorry. Okay, let's talk about that. All right. Temperature is defined by several things. It's defined by pressure. All right. And it's defined by volume within the space in which the particles are. All right. And the pressure times the volume is equal to a constant. The number we denote that with the letter N, and another constant called K, and then temperature T. So in a very low temperature cloud, P and V are very much related to each other. Obviously, it's like PV. Now, when you talk about pressure in space, well, now there really isn't any pressure. The pressure is exceedingly low, even in a dense star cloud of gas like this and dust. All right. So temperature only makes sense when we have enough material to have an atmosphere that can have some type of pressure under volume. Okay, or volume under pressure. And in the heart of a collapsing cloud, we can get some pressure, and thus temperature becomes defined. Again, the equation is PV equals NKT, and that particular formula is one that I'm sure many of you have encountered if you've done any chemistry of any kind, and will have also encountered it if you're doing any kind of work in biology as well, because we would use that thing as well, and that's like the ideal gas law. Very important to understand because, as I said, temperature doesn't really function in space like it does on the Earth because we have an atmosphere under which temperature works, and the air gets warmed by the sun, and so the air itself, the molecules, have a certain level of vibration that's caused by the sun's energy striking them, and this correlates to an increase in the volume. As the temperature rises, we get an increase in the volume because the pressure, if it stays the same and the temperature rises, something has to go on the other side of the equation. All right, so if the pressure stays the same, then the volume has to increase. So when temperature rises, volume rises. Okay. However, if you constrain the volume, all right, and the volume doesn't change, then the pressure has to rise. So as the temperature rises, the pressure will rise. See, because P times V equals a set of constants times T. So temperature is related to pressure and volume. And if you don't have volume and you don't have pressure, you don't have temperature. I know that sounds sort of crazy, but that's what it is. But if you write it out on a piece of paper, P times V equals blah 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 times T. Never mind the blah blah blah, because the most important part of the relationship is T equals P times V. All right. So when you see T on the right, you think those two things have to equal something. They have to be equal. So P times V will equal some T. Okay. So if you have high pressure and low volume, you'll have the same temperature, theoretically, as when you have a low pressure and a high volume. Okay. That temperature can be the same if it works out that way. All right. So temperature is something that is a convenience. It allows us to measure, the entropy in a system. That is how disheveled things are. It allows us to understand a little better how our particles are moving in an enclosed space. And so when we talk about pressure and temperature, then it makes sense when we talk about condensing gas clouds. When it's out in the middle of interstellar space like we see here, the pressure is effectively non-existent in these clouds unless we have concentrations of collapsing parts. And then you can say, well, with the infrared temperature, we can see the infrared temperature of that cloud is a certain amount. Now, the reason we see, when we look with an infrared telescope, vast clouds in this exceptionally cold space is because, and again, infrared is heat, and you would say heat is temperature, and that's true. But what's happening is, in space, dust grains, like the dust grains here, these are solid pieces of dust, and when the star's light hits them, they absorb that energy, and then they re-radiate that energy as heat, because they're warming up, and then they heat that, and then they warm up, right? Because they can be heated up, they can absorb the energy. So when we talk about temperature, when we talk about space temperature, all the things do in space is either absorb or emit radiation. All right. So that's a different ball game. So looking at a cloud like this, we can point an infrared telescope at it and get the temperature of the cloud, because of the fact that the particles are either warming up or cooling off, and we'll be able to map the temperature, different temperature regions within the cloud. And that's how we know that these clouds are very, very low temperature, all right? But they're not at absolute zero. They're somewhat above it. But when they're near a star, the dust grains will absorb radiation, and when they absorb radiation, that radiation has nowhere to go, so it's going to increase the temperature, all right? The volume and the pressure will change against each other, and the temperature will increase. So I think that's pretty cool the way it works. And as Carl Becker says, and 42 is the answer to life, the universe, and everything. Yeah, that's Douglas Adams, of course.
Mark C. Ramos has a question for you also. He wants to know if you are aware of the EULIAA project.
Oh, the Yulia?
It's yes, Project Yulia.
It sounds familiar to me, but I don't know it. No.
European LiDAR Array for Atmospheric Climate, something or other.
Okay.
Development of a LiDAR array measuring autonomously the atmospheric wind and temperature from 5 kilometers up to 50 kilometers on a 24/7 basis.
Wow, that's pretty cool. I wasn't familiar with that. Thank you for telling me about that.
Me neither.
I certainly don't know everything. I'd like to know everything, though.
I'll post a link to it.
Thank you. But you know how the thing is, if you knew everything, you know what would happen? You'd become a know-it-all, and you wouldn't, people would begin to hate you for it. So, you know what? I don't mind not knowing everything. So see the difference between this nebula and the one we just saw before? The one above, just above here, out of shot, is the Rho Ophiuchi Nebula, and this is IC 4602, I believe. This is, IC stands for Index Catalog, and it's a dust cloud. Look at these beautiful structures in here. I'm going to add an enhancement to sharpen the dust. So now let's check out the dust in here. Watch. Okay, I have it at relatively low setting, but you can see that the dust clouds are a lot more defined in here. And this satellite trail going right through the middle of it is just awful. All right, so let me do IC 4602. And it is a dust cloud. All right. Is it going to give me a problem now with that name? Shouldn't.
C. Ramos asked me a follow-up question. What do I think about weather warfare thanks to space weather modification? I don't know. I don't think I've ever thought about it before. I could certainly, and he wants to ask you the same thing. In the future, is it possible? Possibly. It might sound like a Star Trek theme right now. I'm reminded of when, what's her name? The actress from Wonder Years was on Star Trek Next Generation. She turned out to be a Q, and it turned out the Q continuum had her parents killed in Kansas due to so-called freak weather. Tornado came out of a clear blue sky or something of the sort. You could call that weather warfare if you wanted. It's an interesting thought. I don't think we're anywhere close to that.
I agree.
But who knows?
I know people talk about HARP, high altitude atmospheric research program. But, the truth is, HARP does pay attention to ionospheric activities, and that led to people saying that HARP is controlling weather and stuff like that. What they don't understand is that even if they could only control it over their facility. They can't control it around the world. So I don't think that we're able to control the weather per se. And the reason is because of the fact that the technology to do that, the technology to do that is so far beyond anything that we have done to this point. I don't think we have been anywhere near that.
Yet.
I know we can always keep adding yet, and the conspiracy folks love to keep adding the word yet, to it. No, that's not true. They always say, "Well, you're just dumb. You don't know." They like to just play the authority and say they know better, just even because they got their degree on Google. They watch a YouTube video by someone else equally ignorant. They see that a lot. But look, it doesn't matter. I mean, people can believe what they want. That's fine. They're entitled to their own opinion. They're just not entitled to their own science. And that's something where the word yet can't be added to it. Because they can't expect to know everything, and they cannot create their own science. They're not entitled to that. Okay, so this is looking pretty good.
The satellite took an interesting path through the image.
I know. It's like it went through, leaving a trail behind it as it did, and it's probably going, ha, 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 ha.
Well, no, I think it sort of aligns with the clouds in that one star.
Yeah. Ronald says, in counter to what I've been talking about by us not being able to control weather yet, he says, but then again, he didn't think that this remote control, meaning the observatory control, I'm in Connecticut on the east coast of the United States. The observatory is out in the Arizona desert, 2,600 miles from me as we do this. And so he's right. He says, I would not have expected this remote control a few years ago, and we didn't have it. That's correct, Ronald. I spent 2 years 2.5 years working out the details of getting what you see here to actually function. And then I wrote a control program for the observatory, which is right here. Okay. And I'm always running it in the background, just in case we need to. And so I would not have foreseen the capability. That's correct. So that's an example of technology that has come our way. But the weather control, I want to call it opportunity, weather control danger capability has not, as far as I can tell, come our way. Yes, we cloud seed, remember, to make rain. That's about the limit. And beyond that, we'll just have to wait and see where science goes, don't we? Okay, I'm going to dock us up. Go ahead, Daryl. I'm just going to
remote-controlled observatories have been around a while.
Yeah, they have.
And like so much else, I mean, it's constantly evolving.
Yeah, I mean, Hubble was a remote-controlled observatory. WISE, the Wide Infrared Survey Explorer, was an infrared satellite, and it had a tiny little mirror in it to do infrared studies. It was remote controlled from the Earth. Then Spitzer.
Well, I mean, it's been a thing on Earth for years too, and they've been working on it where you could access, remote observatories here on Earth.
Yeah.
Through your computer, the whole 9 yards.
Yeah. But usually, the people that developed them had to spend hundreds of thousands of dollars to get it to the point where it could do that. So as the technology has evolved, we have taken advantage of systems that allow us to do that. And I guess that makes it, easy. And in 50 years from now, everything you see on the screen here will be considered old-fashioned. And remember when they used that stupid thing? It might be very, very different. Hey, look at Marianne out there.
Hello, Marianne.
Yeah, she's there with Diane and Randy. Marianne was fishing with Diane and Randy on a lake out there yesterday, it was. They would have got done a lot sooner, but it was Marianne's boat, and her motor died. I think it was what it was. The motor wouldn't start or something. Oh no, it wasn't tuned to the high altitude. Yeah, that's the excuse she gave. That's okay. What she never said was that they caught any fish, so I don't know. I didn't see any fish. She'll tell you though. Okay, let's save this now. Save it exactly as seen. We'll come out of here. Now, we may not be able to see the obscured globular cluster. We may try. We'll try it. I'll have you give me those coordinates again in a little bit, but we're going to go to measure 4 right now.
Oh boy.
Yeah. Wait, let's measure 4 is right here. It's called the Crab Globular Cluster. I don't know why it's called the Crab. I guess that's because that's what they do. Alright, now let's go there now. We'll go to the Crab Globular Cluster, known as Measure 4. And let's, first of all, go to our low light mode. And when we do, we'll probably already see Measure 4 in the view. There it is. We'll take the opportunity here to also do another focus run. So I'm going to defocus the stars, the little donuts, and we'll focus again.
Cosmic Ray says in 1996 he logged into the TIE telescope, the TIE telescope, on Mount Wilson with a 19.6 baud modem and imaged with it.
Yeah.
So
And
there.
just how expensive was the equipment that was at Mount Wilson's end? Millions of dollars. My point exactly. You couldn't do it at home. All right. We're going to go here and do this. Now we're going to do our focusing run.
Mark Ronald's asking you about the new telescope. He's had a couple of questions.
We're able to test the new scope yet. Yes, I did, Ronald. As a matter of fact, I showed it on one of the streams to everybody. And you saw the telescope, saw it moving. I was moving it from here in Connecticut. The new system is more robust than the current system we have. And so we're actually going to convert the new system. I'm sorry, we're going to convert this system here to the new system as well. We have a second mount identical to the first one that we just bought. And so the telescopes will run the same exact way with the same exact software. Because remember, the goal is we want to have two telescopes up and running simultaneously while we're viewing objects. This will be the wide field view, and the other one's going to be the magnified, what we call a higher focal length view. And that's really, really important to do. So we can compare, like, say, what the very core of a globular cluster looks like versus the area around it. And we'll have both of those images available for free on our server. I thought you were in the. I thought you were in that show, Ronald. That. I think you were. All right, we should see a line right about here in a second. There it is. That's our focus. Best focus is a parabola of focal points, and these are the discrete spots that the focuser focused to, right here, right there, and it made a curve. And the bottommost part of the curve, as you can see, isn't necessarily going to be where one of the focal points was. So it interpreted where that is and made that the focal point. And as you can see now, our stars up there are beautiful pinpoints. And when I get out of our focus position, all right, there you go. You can see it beautifully right now. And I'm going to just bring it up a little bit. And I'm going to do something interesting too. I'm going to move it a little bit to the west. And no, east, I mean. I'll tell you why. Because I want to start to show some of the Antares Nebula, which is out here in this region. The star Antares has, it's embedded in a lot of dust, and it's illuminating a lot of the dust. Okay. So from here, we'll set up for a 25-second shot again.
Izabela has a question of you. She says, Mark, there's a window that slightly obscures the clock on the telescope windows. Is it possible to move it?
Oh, you're right. Thank you, Izabela.
She uses it for the table of contents.
Yeah, thank you, Murray. All right, let's just do this here. Get that. You're right. Sorry about that. That was my telescope program that was in the way. I also have a clock on screen that I should put up there. And I do have it. And it's should be visible up here. Let me just
Mark,
try. Yeah?
excuse me a moment, please.
Okay. Okay. Well, I'll have it for next time. I'll have that, so no problem. I was getting complaints that it was on the screen and bothering the view. All right, so 25 seconds off and running. Let's go stack this now. And let's get out of low light mode and go into deep sky mode. Yes, right there. All right. So yes, I'm gonna play you some of the music at some point that I've been making for SkyTour and so forth. Oh, look at that! That's really pretty. Okay. And from measure 4 here, there's another one right there. Isn't that pretty? Look at that. Now we zoom in, and the stars are beautiful pinpoints. There we go. When this noise is going to go away, actually, I can probably get rid of a lot of it by doing this. We don't need this one right here. All right. And take down this value here. This is the mid-level. And so we should be able to get it a lot better looking. So we can actually see right to the core of this cluster. This is measure 4. It's a globular cluster. I've mentioned this many times. It's a halo object. These globular clusters and galaxies have hundreds or more of them, and they many times may very well have a black hole in the middle as a seed that was the thing that built this black hole. I'm sorry, built this cluster. But you know what's funny is they orbit the galaxy from outside the galaxy, so they plunge through the disk and they come popping out of the disk. This is measure 4. It's very close to the galactic disk, and it's plunging through. And what might happen is some of the outer stars might get lost and pulled away by other interactions. Some of the stars may be actually left behind, right? So this particular one, its distance is 7,000 light years from us. 7,000 light years. So it's more close to us than it is to the center of the galaxy. We're approximately 30,000 light years from the center. This is 7,000 light years, a little more toward the galactic center. And then this one here, up here, let's take a look at how far that one is. And to do that, we have to go grab it. Let's just check it out. All right, this one is a distance of 29,000 light years away. So what that tells us is that when we look at this screen, you can kind of tell it's farther away, right? It looks dimmer. Well, that's because the intensity of light falls off as the square of the distance. So if you're twice as far from something, it's 4 times fainter. If you're 4 times further from something, it's 16 times fainter. 2 squared, 4 squared. And so here, this is 26,000 light years away. This is 7,000 light years away. Clearly different. Smaller, but they might be the same size as this, but once you brought it closer, they might look the same side by side. All right.
And 4 is also the closest globular to Earth.
That's correct too. You're right. You're right. I did not recall that concept. You can see red up here. That's actually the nebula from the Alniat star. Alniat is kind of near this location. So if we come up here, you can see Alniat right here, and you can see this nebula which kind of extends down. And when we're looking at M4, right, if we center on it, all right, you'll notice that we have a tiny bit of this nebula that's going to be visible here, which is not visible in this. You're not necessarily getting really good imagery in this stellarium planetarium, but we can clearly see that there is some more stuff in here, and you can see some interspersed throughout here. You see all kinds of red nebula. This is coming from the Antares Nebula to the east. And to see that, if we come back, you can see the Antares Nebula here. And the Antares Nebula does pollute our view a little bit, and that's what I wanted to show you. And so here on this edge you can see that we have Antares Nebula in here. That's pretty cool. Alright, we're just going to get a 12 shots here and then we're done with this.
I like Messier 4 because we see that line of bright stars nearly vertical across the face of it.
Right here.
Yep.
Yep.
Every globular is different.
Yep. Every globular has its own personality. Alright. Let's just save one more time now. Or save for the first time now. Alright, save exactly as seen. And there we go. Okay. So let's go back into our low light acquisition mode here. Here we are.
Ronald, it's a globular cluster.
I know what you're saying though, Ronald. You see a cluster here, you see a cluster there, so are these like a double cluster? Yeah, no. They are actually, just as Daryl said, it's a globular cluster. It's 7,000 light years away. This was 26,000 light years away. This was very prominent. That one you can barely see, right? In this light, in this low light mode. Okay. So let's come back here now. So we're past the meridian by quite a distance now. So if we go this way, I'll bet you we can get to that other globular. What was the actual name of it?
Stop right there for a second. Can you pull it back up a little bit? Or pull it back down? You see all those yellow circles with the crosses in them? Every one of those is a globular cluster, folks.
Right.
Okay, and you wanted to see that Terzan 5?
Yeah, I don't know. What, do you have another designation for it?
That's what whoever asked for it was.
Okay,
and
well, let me have the...
That's what came up in Wikipedia.
Okay, so 17 hours and...
1748.05.
All right, 1748.05 is in. And what's the declination?
Minus 24, 46.48.
All right. Well, let's go there. Go to. Okay. And let's see where it is in the sky here, and let's see if let's back out a little bit. It's going to be over here somewhere. There it is. Alright, so it's in here. It's not even listed here.
Can you back out again a little bit? I wanted to see the constellations, exactly where we are. Yeah, your center of the galaxy is just below it.
Yeah, that's what I was saying. We're very close to.
Yeah, that's why they say it's so heavily obscured.
A. Well, here's what I'm going to do while we're here. Let's go in and get some more data. We'll go to DSO, Deep Sky Objects. Let's go get some Caldwell objects if we've got any here. Barnard objects. These are the dark nebulae. Sharpless catalog. We'll get Lund's Bright Nebula. Lynn's Dark Nebula, sorry. Alright.
Has like 2 million stars in it. Pity we can't see that. I mean,
well, let's find out if it's visible at all. Let's find out.
Omega Centauri has like 4 million stars in it.
Okay. Well, theoretically, it's in this view. So let's do a 25-second shot. All right. It still says we're searching right now. There could actually be too many stars for it to actually guide on, and not enough bright stars, which I think is problematic for systems sometimes. Now we'll clear this. Alright, let's see what we get. Heavily obscured. This is a beautiful shot, though. Let's zoom out a little. I wonder if it's that.
Sure is red.
Yeah, it could be reddened. I think that looks like the globular. You know? That kind of looks like the globular cluster, doesn't it? Heavily obscured by dust, which will redden it, and that's what we might be seeing here. That's actually an interesting object. Let's go back to our histogram. And
it is approximately 19,000 light years away.
Through lots of dark dust. Let's pull this back.
The apparent magnitude is 12.8.
Okay. Yeah, that looks like it.
2009, it was discovered that Terzan 5 consists of at least 2 generations of stars with ages of 12 and 4.5 billion years and slightly different metallicities, possibly indicating that it is the core of a disrupted dwarf galaxy, not a true globular cluster.
Interesting. And we have a tumbling rocket body over here that has glintings going on its surface.
Terzan 5 is thought to be a fossil fragment from the assembly of the galactic bulge.
Well, that's it. I'm pretty sure that's it. It's definitely standing alone. Fantastic. I thought that was a good one. We're gonna make a note of this one, and we're gonna call it Terzan 5 and GC. So that's cool. That's a neat. I like looking at new objects.
Yeah, this is one that would benefit from some more focal length.
Oh yeah, and longer exposures. But it's okay. This is a really neat one. As small as it is, we're peering into an amazing depth of the universe here. That's pretty cool.
Can you go back to...
You can see this dark nebula too that's in the way of it. Stellarium?
Yes, for a moment, please. Back out a little bit. Okay, you can see tip of the spout of the teapot there is our nozzle.
Here's Bates out the window.
Yeah. And then the bowl of the...
I'm going down there.
Get a little bit more to the right. We can see the bowl of the Pipe Nebula. Back out a little more. There's Sagittarius A West. There's the bowl of the pipe there at the upper right. If you draw a line from the nozzle to the bowl of the pipe, center of the galaxy is right about halfway in between the two. So just about where the upper right-hand corner of Mark's image frame is, or was.
Oh, right here now, from here to here.
Yes.
Yeah. Yep. There's Sagittarius A West. Yeah. Pretty cool. All right, well, we got 11 in here. We're going to go to 12, and we're going to end at that. There we are. Okay. Not bad. That's pretty cool. It was a nice to see anyway. It would have previously been something we could never even possibly have seen. All right.
Michael H. has another question for you.
Oh, that Michael H. Always asking questions. What's wrong with you? What's wrong with you, man? Always asking questions. Okay. Starting to use a microscope. Have you found the similarities between the miniature world and the universe? Oh, very interesting. Well, first of all, it's all made of the same material. The atoms come from the same places, right? The atoms in the universe come from exploded stars, by and large, and the same thing for all the microscopic animals. I do have a microscope, and as Izabela was suggesting earlier, I have been tempted to make streams for microscopic stuff, so we can show really cool creatures in pond life and stuff like that. I have a lake right down here that my house overlooks, and I could go get a jar of pond water and check it out, and you'll see things moving in there that you just will never go in the water again. Okay, pretty cool. All right. I'm tempted. I've been thinking about it. It's just that I do have to sleep sometime. But with the advent of the solar observatory, I may not get a lot of sleep as it is, because we're going to be studying the sun quite a lot too. All right, let's go in here. And we're very close to the Trifid Nebula. We're going to jump up to that. Alright, so here we go. And from there, we'll jump down to the lagoon. There's just so much to see. And boom. There's the Trifid Nebula, otherwise called the Trifid. Tri meaning 3 lobes. You can see 1, 2, 3 lobes basically, separated by dark nebula. That's just dark dust lanes that are superimposed over a nebula. The nebula is not broken up like that. The dust lanes are just coursing through this side of it. So we don't know how far into the page it goes, so to speak. Alright. So we're going to do another 25-second shot here. And we're going to go into our deep sky mode. This is a gorgeous object because it shows 2 different aspects of the universe happening all at once. Okay? That's actually a very pretty picture. I'll clear it now because we've already saved it. What the Trifid Nebula shows is a red nebula created by ionization of hydrogen, and when it glows red. And the blue is scattered starlight, so look at that beautiful thing, where the hydrogen gas is either not dominant in that area or thinner, lower density, and therefore doesn't ionize as strongly as it did here. Okay, and if we zoom in a little bit, you'll see very clearly, in fact, we're getting some gorgeous detail here. I'm going to turn on our enhancement again here. Okay, so now we can see even more detail on the nebula structure. Now, backing out a bit, if we look closely, you can see subtle red areas. This is not, an artifact. This is actually subtle red glows of what's called diffuse hydrogen that's spread out in the interstellar medium, and it's glowing red because it's ionized from nearby hot stars. And these two stars in here are likely the ionizers for a lot of this hydrogen. You'll notice that the nebula is sort of spherical. That's because that ionization potential goes out a certain distance in all directions around the star. And when it cuts off is where the temperature has dropped low enough so that ionization no longer occurs. And so you expect to see a boundary around the nebula, all right? And if you have a lot of stars and not just a couple that are in there, then sometimes it's all spread out, like in the Lagoon Nebula, all right? Here, though, the Trifid is these two hot stars in the middle. They're ionizing much of this cloud. And then up here, where there may be hydrogen, you have a star that is not hot enough to ionize the cloud of gas that might be around it. However, what's happening is the starlight from both here and here are striking the dust particles, and the dust particles are scattering the blue component of that light. It's happening all throughout here, but here the hydrogen is dominant and really blows out actually all of the blue glow because it's subtle. But you can see on the outside edge where this ionization potential has dropped off, you can see this blue all the way around here. See that? And that's exactly why it's there, because it's throughout, all right? And the stars can have their light scattered by the dust and out to about here for this particular nebula. So we'll go
Mark,
by.
Zoom in on the nebula a little bit, please. I wanted to see something a little better.
Okay, hold on one second.
The red hydrogen nebulosity appears especially intense sort of at about 4 o'clock.
Oh, over here?
At about 4 o'clock, yes, right there.
Okay, well, let's go see it.
And actually, if you can zoom in some more.
Oh, I can see we have to... I see we have I have to lower this number.
I'm wondering if I'm seeing things I haven't seen before. One, there right at about 3 o'clock, there's a kind of a bright bar going from lower right to upper left.
Oh, here.
Yes, and I thought it was actually going behind the horizontal cloud, but I see that's just stars. But then down at about 6:30 or 7 o'clock, there's a very distinct little snaky curve of nebulosity. It's dark, and then this light on the upper side.
And this one?
Yes, exactly.
Yeah, that one I've seen many times. That's been there. Look, see the stars. I had the full width half maximum level too high, so I know this is gonna make you angry. Not you, Daryl, but everybody else. So I'm gonna start over, and now that it's lower, it's been in action for now the last iteration. So this would be a perfect one. And so now we're gonna make sure that all the incoming images are gonna be below our just about 8. So I have it set to 8.16. And so any that are over that will make the stars elongated, and I don't want that. There we go. Izabela asks, when the dust is condensed, can it cause back pressure on the nebula and restrain its expansion? Well, keep in mind, that's a very good question. Keep in mind that when you have a condensing area of dust, it's going to be resistant to a lot of things. It's going to be resistant to erosion by hot, bright stars around it. We see this in the Rosette. We see this in the Cave Nebula. We see this with the Comin Nebula. We see this with the Orion Nebula and the Horsehead. Almost every nebula. We see it in the Eagle Nebula. and the Omega Nebula, in fact, as well. So we see that it actually does, show that it has resistance to being eroded. All right, and that's very important to pay attention to, just like you're suggesting. But by back pressure, I think I know what you mean by back pressure, and I don't think it would be considered a back pressure, but more of a resistance to erosion. Because remember, there's no the biggest source of gravity in that area, that region, is the area of the cloud itself that's self-condensing at that point. All right.
If you want to see where things get mixed up a lot, gas clouds and filaments and stuff, just look at the veil.
Yeah, and hopefully we'll get to the veil tonight. Because Ray's always asking for it. I figure we got to go show Ray. See, there's no spider here, so it can't keep us away from the Cygnus. So this is beautiful. See, now our full width half maximum filter prevented us from losing an exposure and getting an elongated stars because of a spate of wind that popped up. So let's see if the next one comes in or goes even higher. Yeah, okay, it went away. So it was a gust of wind, would have ruined our whole shot. Look at the blue around this. See the blue? This blue now, something that's been hard to detect in the past with us. Our past camera, which was a ZWO ASI 294 MC Pro, that's just the designation. This camera, the previous camera, could not see very clearly this material around here, nor could it see the details in this nebula. Look at this detail within here. I have the enhancement on, right? Okay, here. And if we just click that up a notch, all right, look at how sharp and clear these singular little lines are. These would not be as clear with the past camera. And I will say this right now. What you're seeing is the first time, second technically, because I shot it last night, but the first time that this particular image has been captured with this new camera, which is tuned to this telescope. So this is the best possible representation for our aperture versus our sky and our optical setup with the camera. That's really pretty. Lots of nice subtle detail up here. Look at this little separated piece here. That's something we wouldn't have seen either. We need to compare past images of the Trifid Nebula, and unfortunately there probably would be the other 296 MC Pro. That's alright. I'm going to go into our histogram shot right now, and I'm going to zoom it. I'll tell you why. I want to have the leeway to move this guy way down, because I want to close in on looking deep inside this nebula. See that? This helps us see some of the detail, guys, within the nebula. You know, it also reduces a lot of the noise. And at a certain point, it actually helps us. Yeah, so I'm going to pull this back a little bit. Alright, here we go. Like right to here. Right, and let's pop this up just momentarily. Yeah, you can see a lot of stuff going on in there. Okay, let's go and look at a negative of this image. Now you can see very clearly. Look at that. You can see these beautiful structures in here. Look at that. such convolutions. That's absolutely pretty incredible.
The blue part is the red part now, and the red part is the blue part.
Yep. And if we actually just take it down, then we can see a true black and white image right here. I took the color out entirely, so that if we come back down to like the proper image, you can see what this would look like in a black and white image. We would be robbed of knowing where the reflection nebula started and stopped, and we wouldn't know that this was reflection nebula around the outside edge. But by bringing our color in, we can do that. There we go. What's funny is, for years I had a poster of the Trifid Nebula in my room. I would hang it up all the time. It was a giant poster. And it was taken with the 200-inch telescope at Mount Palomar. And I just loved it. It was just a beautiful, an incredible image of the nebula. And I always wondered about the blue part. But what you don't see in it is the blue that is down below here. You don't see that, which I find interesting. Now I'm going to do a color correction. We haven't done one in a while. And now we're going to do there we go. We're going to do that. So now, if we zoom out a little bit, you can see how the blue literally extends out here, comes down here, goes all over here, out to here, and up there. Look at that. It surrounds this whole nebula, and this is the ionized part here.
And the blue is all Rayleigh scattered.
That's right. The blue is scattered blue light. Now, the way that works is very interesting. You know, I talked about these dust particles being microns in size. The microns are very, 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 very small. Okay? So, they easily absorb the blue light and re-radiate it away. Okay? There's just it's the frequency that's perfect for these dust particles to absorb and re-reflect immediately. The red light, not so much. Okay? So, I had the thing that's interesting is when you look at what happens, those little tiny dust particles will take in the light from the star. The high frequency light is the blue light, and that high frequency light is just the right frequency that those dust particles like, and so it'll take it in and reflect it back out. It's like, yeehaw, let's send it back out. But it doesn't really take in the red light. They kind of let that pass through. So that's why we see it this way. And that's why we see blue nebulae. That's why we see the blue color in the universe. It's also why we see the blue color in our sky, because our air molecules are doing the same thing with the high frequency light coming from the sun. All right. So that's why that happens too. I'm going to change this to Trifid Nebula. Okay.
I saw a pure red rainbow once.
Just red?
Just red.
Hmm.
I was up in the mountains. A storm had just passed.
Yeah.
And the very last rays of the setting sun lit up the storm to the east of us.
Wow.
And it made a rainbow, and all that was left, literally, was red light. So all we saw was a red rainbow.
That's cool. Izabela says the dust lanes here look like a harness that sort of holds in the nebula. I think that's kind of clever. Now, she's also a very good artist, so I could see her thinking creatively out of the box like that. That's very cool. All right, let's back out just to show you the whole area.
I could kind of see that. Looks sort of like a horse's bridle.
She's right. So you see the rest of this. Now you see this is just a stunning stellar region. And we jump in here again. Come in here. We'll go to like 50%. This is 50% or so of the of the magnification level for our sensor here. I'm going to pull this down a little bit. There we go. Look at this detail, Daryl. You can see this sweeping motion in here. You see that?
Yeah.
Sweeping motion. And it's duplicated.
I almost see that red band going behind that cloud on the right again.
Well, I see it going this way.
A little bit of it peeking up above it.
I see it doing this. Well, this red stuff is behind the cloud, so it is going behind. There's no doubt. There might be some mixing. We don't know how far in, but it's just incredible. Now, keep in mind, guys, this is light years across. This is many light years across. All right. So if you were in this, flying through it in the spacecraft, you might not even see the red glow, because the atoms of the hydrogen that are actually here, they're actually ionizing. Those atoms are so few and far between. You might only have 30 per cubic centimeter. All right. And we have something like 10 to the 19th atoms per cubic centimeter in the air. So 30 atoms per cubic centimeter. You need light years of these in space to even be visible from a distance. And it would have to be from a distance. So that's pretty cool. This is really stunning. This is stunning tonight. Let's take a look at the cloud problems if we have any. All right, the other clouds are gone. Good, we got a great night. We're going to take advantage of it. All right. And yes, we're going to go to Cygnus. All right, so we'll save this here again. There's 16 we took, 13 have been rejected. That's good. Our full width half maximum's doing its job. I am being rather tight on the constraint here. I want to make sure that we are going to be under 8.16, because at this elevation, where we're near the relatively near the celestial equator, it would be difficult for the tracking to show round stars with a high number here, because we would allow too much movement, and so the stars will move. Geez, this is something. I don't want to stop looking at this. It's so beautiful. Let's be crazy. I'm going to zoom way in, right to the center. Fill the screen with the red. Look at that. That's incredible. Wow. That's really pretty. And then up here, we have detail up here. You can see some really nice detail in here. Let's go back to the histogram, and let me pull that down just a little bit more. It's going to get a little dimmer, but we can see more of the separations going on out here. Now, let's see if we can utilize this guy a little bit. That other one's really drastic, but still, look, you can see a true separation. This is in front of the blue, there's no doubt. And if we back out and just check it all out, look at that. That's really pretty. Okay, well, that's good for now. We got 22 of those. Okay. $23, we'll save. Nice. Wow, that's pretty. I hope you guys enjoyed that one. That's a gorgeous nebula. All right, let's say goodnight to it and go into our low light mode again.
Nice picture.
It's beautiful. All right, and now we're going to come out of here and go back into dark sky mode. I'm sorry, low light mode. Here we are. Oh, you see that little movement there from wind? Okay, and now I want to go south, but I know where I'm going. So I'm going to take us to this next object here.
M8, of course.
Yeah, because it's right nearby.
We hardly ever look at M6 or M7.
No? Yeah, it's true.
They're farther west, over above the tip of the scorpion's tail.
Yeah. All right, let's I'm gonna not look at wait, going the wrong way. I'm not gonna look at the Chinese dragon, because with the previous camera we could actually encompass the whole lagoon plus the Chinese dragon nebula, which is off to the east out here. It's like right around, well, it's off the page from here. Okay, but let's let this get in. Let's check the stars, make sure they are focused down to the smallest. And they are. Excellent. Alright, so this is the Lagoon Nebula, a true stellar nursery. Now, unlike the Trifid Nebula, this one is more extended and distended, okay, because there is in here, in this hourglass-shaped location within the nebula, is this O star. And this O star is literally lighting the entire core of this nebula. When that O star goes supernova, it'll light a lot more gas briefly and dust, and then it will fade. When it fades, it'll leave a remnant, and we won't have this bright part of the nebula anymore, unless that supernova kicks off stellar formation. Alright, so let's check this out. So this will be another 25-second shot, and I think you'll approve. So let's go into deep sky mode. Now that we know we're here, we're already guiding, you can see here. So we come in here and we will get rid of our last image of the Trifid Nebula, which we had saved. Okay. I want my stack. That's really pretty. Okay. We'll clear the Trifid Nebula, because that's up on the server already. And now we will see the Lagoon Nebula in all its glory. And here it comes. Ah, look at that. Isn't that crazy? What a beautiful nebula this is. Now, that hourglass thing I was telling you about is right here. You can see the hourglass here and the O star sitting next to it that is illuminating this whole region. Let's color correct it. And then we can drop this down as far as it'll go to lower the brightness in here, so now you can see that more clearly. And notice the dark nebula in here, this beautiful dark nebula. Look at these little subtle pieces. Again, this is the first time I'm imaging this actually publicly, so it's pretty cool. And you can see these details that just eluded us with the last camera. Wow. So we'll zoom out. And it won't look as bright because I did lower the brightness in the center of the nebula, just so you can see the core of the nebula is illuminated by that star. Other stars in here formed in this nursery, illuminating other parts. All right, and if we give this the processing it wants, you'll see this major difference right now. Pow. All right, that's impressive. Wow. That's one thing this camera does better, Daryl, is the reds. The last camera wasn't tuned, so it didn't do the best reds, but this does. Okay.
The reds are real. You should keep them.
Well, I know that they're real, and I'd love to keep them, but they're elusive sometimes. They're elusive and aloof. Look at that, huh? Let's see what our full width half maximum filter that keeps us looking at round stars is telling us. Oh, that's interesting. Oh, hang on. That's what I had to do. There we go. So one shot violated our range. Stephen Smet in Belgium, Mr. Django, says the colors. I agree. The colors are fantastic. JSCO 77. Nice to have your own mini Hubble. LOL. It is really pretty. You're absolutely right. And what's nice is the ability to show what might take many minutes to produce is, I think, the win-win. Because you guys are spoiled. You don't have to wait many minutes to see it. It's right here in front of you. Within seconds. 25 seconds, as a matter of fact. Look at that, Daryl. Look at this very subtle detail in here. Look, I've never been able to see that. Michael Hedrick says, "Oh my word! Why can't I just use all caps and go crazy?" All right, Michael, get it out of your system. Go for it. You get one shot. No worries. No one will penalize you. You're a good friend of SkyTour. I mean, this is just amazingly well beyond anything I ever thought was possible on Earth without a huge telescope. Agreed. And working smartly with the equipment we have is why we can do this. You know, getting a very low focal length out of this is really something that's important. And we got a wide field out of it, and that allowed us very fast operating, optically fast telescope. And this is the Lagoon Nebula, otherwise known as Measure 8. Vincent Virtues is with us. Hey, Vincent. Yeah.
Look at some of the loops and whorls and stuff up above, up at about 12 o'clock.
This stuff?
Yes, that one there in particular.
Yeah, this one here is really nice.
Yeah. Can you go up in the field a little bit?
Yeah, of course.
There you go.
I also want to point out something else here, and I might have to zoom in a little for this. I'll keep the other one in there. I want you to notice the texture in here. Look at this texture. All right. That texture in here is real as well. Now you'll see that it's got blue in here, it's got red. So we can expect that there has to be oxygen in here that's getting ionized. And so it's probably doing some of that as well. We're also getting dust that's going to be doing Rayleigh scattering, so we are getting this blue reflection component as well. Everything is going on all at once in this nebula, all of it, everything. This is looking remarkably 3D. You feel like you can just crawl right over this ledge and peek into what's beyond. It's crazy. It's crazy. Now, you know what? I'm gonna lock this off, and I'm actually going to get rid of this. All right. Well, I didn't mean to get rid of that. That's not what I meant. So I want to do the. Go away. Stop it. I want to bring back my image. Oh, I think it's going to go away again. Yeah. There was a delay. Sorry. Okay, here it comes. Wow. This is beautiful.
Ray, the color's real. It's emission nebulosity, and the colors are representative of the elements, the molecules, the gas,
Yep.
emission frequencies, wavelengths, whatever.
Yeah, this is H alpha. It's actually red. I like this. And these colors are all actual colors. And this is why I'm glad we're not looking at this in black and white. Because if it was black and white, then we'd be looking at it. It'd still be impressive, but we'd be looking at it like this. Okay? Still impressive, but you know. We could take a negative of it and look at the details. Look at that. This is why we use black and white a lot, because they showed us many of the details in the cluster. And this is stuff you don't really readily see easily when we're outside of the negative realm like this. Okay. Alright, so what we'll do now... See, this is why I like color, because in one shot, we get to bring you this. And I'm telling you, there's no outdoing that. Welcome to the Lagoon Nebula, folks. This is 11 stacked and 10 ignored because our winds have kicked up a little bit and prevented us. So you see it's sort of like, let me just zoom out of this a little bit. So you see it's almost all the same. Good, we got more. So here's a full dozen frames that have stacked. You know, when you look at this, as an astronomer, when I look at this, I see the dark nebula regions, and I know what that looks like. You know, in the reality we understand of it. I see this bright region in here. I know what's going on in here, astrophysically with the high temperature emission from this O star ionizing the nearby clouds. of gas. And I see the soft reds. I know what's going on there. I see these clumps of black that are self-condensing under their own gravity. You see one right here. Okay, actually, let me show you that. So you look at this one right here. Okay, that little guy is a globule, right? And this globule is a globule that is condensing under its own gravity. And someday there might be a star that winks on in there, along with a retinue of planets. Okay, and if we look elsewhere, we see them like this one right here. Yeah, that's a larger one, and that big one could be spawning several sets of stars in there. This one is really fascinating because you can see it's got a black, like a comet nucleus almost, and it has this fan of material behind it. Now, why is that happening? Well, that's happening because some star somewhere is actually probably pushing this material back, these dust back, or did at one point. It might have been maybe this star, okay, or maybe it was this star, and at the time that the star was more aligned with it, maybe it's pushing it back, and we don't know whether this is just doing that, going straight down or coming out at us. Okay, notice another one right here. There's one right there, another fan-shaped object in the same exact amount. So somewhere there's pressure hitting the dark condensing head of this dust that's sweeping stuff out behind it. And that's the really cool thing. And again, it's not our hot star here, it's not our O star there. It's got to be something up in here somewhere. Now, mind you, seeing a star like this, we don't assume that star can be very powerful, right? But it could very well be that star causing it. We don't know. We have to look at the spectral types of these stars, how much their stellar winds are pushing, and that happens quite a bit. Now here's something that I haven't seen before, Daryl. Here on the right side, you see this wisp, right? Well, look at this pillow of ionized hydrogen. Look at this dark nebula with a fringe of ionized hydrogen.
Yeah.
Look at this. It almost reminds me of the caravan in the Elephant's Trunk Nebula.
Uh-huh.
So that looks so three-dimensional. And then we have this blue reflection nebula mixed in with this ionization going on here. Wow, this is really so good. We'll zoom out now and see the whole thing. This is beautiful. Let's see how much is here. We're going to kick this up now. That's pretty cool. We're actually capturing most of the details in this region. There's a beautiful blue reflection nebula up here. Little fringe. Okay. So the hot young stars throughout this cluster, this stellar nursery that have formed, besides this O star, are responsible for doing a lot of this emission ionization that you see here. Let's let me just do a color correction on this. So I go to histogram. Let's do a color correct because I got a little blue background I want to get rid of. There we go. Now you see the nebulae more. See that? Look at this. It's such a rich, vast area. It's amazing. Then I'll drop this back down and then use the more appropriate way of pulling this up. A little more control. Wow. That's amazing. That's just looking so incredible. Look at this beautiful nebula. Wow. Now, some of you may have this projected to your television, and so you actually see a huge amount of detail on the screen in front of you. And so what I'll do is I'm going to save this here as there's 20 shots here. I'm going to save these and save exactly as seen. And redock our guy here, and let's bring back the telescope view. Okay. Okay. Oh man. Okay. Save one more time. And then let's go up north. So you guys think this is pretty, huh? I think what you're going to see next is actually quite impressive. Okay. Okay, that was beautiful. And that, we're going to go into our low light mode again. And if you go here, SkyTourLive.org, you'll find our new website. Looks the same, but if you want to support us, there's a donate button now. You can donate any amount, even 50 cents. Okay. You can also go to our store easier. You can connect with us easier. And it really is very helpful. And it's SkyTourLive.org. Okay, so there is our view there. Let's now go from here. Let's ride up the Milky Way, shall we? And I want to go to one place in particular, because Ray had mentioned something about oxygen and so forth, and yes, it's not quite the colors we're seeing here, but here we're going to see oxygen 3, which is doubly ionized oxygen. Let's see if we can get there. There we go. Telescope's on its way. The screen has a slight delay from the telescope motion. Here it is. Yep, the Dumbbell Nebula. Yeah, don't worry, we'll get it back. Okay, now we'll head west. And here comes the Dumbbell Nebula. This is a planetary nebula. It's a remnant of a dead star. And the star that's dead is a white dwarf. And you'll see the white dwarf right in the center in just a minute here as we get closer. And we'll zoom in on it. And we'll check the focus again, because as we tip the telescope up higher, we get a phenomenon called mirror flop. Every telescope does it, not just ours. And so we have to refocus just to be safe. So we're going to do that. Okay.
Please hit the thumbs up, folks, if you like what you're seeing.
Yeah. Daryl and I worked very hard to bring this to you. Nice. So now
I'm not doing anything. I'm just comic relief.
comic relief. No, you're not. You're just comic. If I drink all this water, I'm going to need relief. All right, so we're going to focus here on the Dumbbell Nebula. All right. Yeah, Ray's, you're looking at the stacks out of the sea star. And that's fine. I mean, what we're saving are the same types of stacks that you get out of the sea star, just more detail, more capability. But, I mean, the sea star is a tiny scope compared to this. But still, it allows you to capture things, that's for sure. But, you know, the thing that's interesting is that you get the raw images, and if you don't process them further, well, then you get the noise that's in there, you get the other stuff. But if you actually have a resolution that you can process to, then you'll find that you have a much better image in the back end after you're done processing your stack. You always have to process a stack if you want to get the better quality. But, you know, if you don't know that it can look so much better, then you might never make it look better. Okay, we're all focused again here. That's good. That was quick. All right. So we're going to zoom in right away because I know this is a beautiful object. And it doesn't need more than like 10 seconds. But I'll go, I'm going to go 15 seconds on it. Because we want to capture the outside halo of oxygen 3, the greenish blue here that you see. Alright, let's go into this. Go into low light, go into our deep sky mode, I mean. Let's see what our full width half maximum numbers come in at. I would expect them to come in at 6. Yeah, there we go. So I can drop this down to right about there. Okay, first things first. Let's... Oh, that's beautiful. I think this is close to the first time I've seen this one here. Alright.
What did you do to make it so blue?
I didn't. I'm going to, okay. It actually made it blue.
It's always been green before.
I know. Isn't that weird? Let's move this one down so we can see the white dwarf in the center there. There it is. This is really detailed though, Daryl.
When you see the red in this one, folks, it's also mostly hydrogen, but there's some neon in there too, which also has a red color.
Yeah, the hydrogen alpha is interesting. I think I see. Okay, so there's the white dwarf right in there. That white dwarf is the size of the Earth, and this is however many thousands of light years away. I forget. It's only like 1,500 or 2,000, right? Isn't it? It's not that far away.
I forget. I'd have to look it up.
Well, I think we're here, so I probably should be able to look it up. Distance is about 1,000 light years. 861, it says.
Well, it looks like.
Yeah, sorry. Wow, so there's this outer rim here, but you see a further outer rim. So the way this works is that star was a normal star like our sun. Then when it ran out of hydrogen, it puffed up into a red giant. And later on in its years, it started to shrink and grow and went through something called thermal cycles, where it would actually do thermal pulses. And these thermal pulses would push material out. Now, the star may also have been a relatively rapid rotating star, and that could account for this shape we see here. You notice it looks like an apple core, and that becomes really evident when we start getting rid of all the dim stuff and show you only the brightest stuff. Okay, so if we come in here, you'll see that now we're going to see it looks more like just an apple core, the middle of an apple. Okay, so we come in here, do that.
Michael Hedrick has a message for you.
Okay. All right, so there. So what's happening is the star may have been doing like a top, where it precesses on its axis like a top does as it was dying. And if it did that, it could have drawn out these areas. This is the star's east and west equatorial region, and this is the north and south, very likely. So as it rotated, much of the material from the equator, as the star rotated into these thermal pulses, pushed out and made that. So we got a lot of this hydrogen here. This is odd, but this could be the area where it last stayed, where it last reached in its precessing cycles of rotation. And so that could be the material that is, maybe in some time in the future is going to be over here and dragged out in this direction as well, for all we know. It's very possible. So, okay, Michael Hedrick's saying, breaking the rules again, all caps. Thanks for tonight and a new way to donate. Don't say how much, but I just gladly paid your internet, sir. Thank you, brother. Thank you so much, man. That was so kind of you. I appreciate that. We appreciate that. It's all very important for us to do this for all of you guys.
You can pay for my internet too if you want.
That's the Darrow Corporation, right?
Yeah.
This is really pretty. Look at that. Wow. We are seeing lots of detail we've not seen before, guys. This is stunning. I'll change this name here. It's a Dumbbell Nebula. Wow. Okay, 21 shots. I'm going to save that here. Go a little longer on this. Oh wow, it's 2:14 in the morning. Yeah. See what happens?
Yeah.
You don't know what you just don't realize how much time is passing. All right.
Yep, I started turning into a pumpkin a while ago.
Okay.
It's after midnight here.
All right, so I'm gonna look at our sky. There's our Milky Way. This is a color image, obviously. So you can see now we're up in Cygnus. We're right about here. Okay. There's Deneb Oh, see, gonna have to turn those off because Deneb is here. Then you have the rest of Cygnus, Deneb, Gamma Cygni here. The this here is where the beautiful Veil Nebula is. And over here, and here we have the center. This is Gamma Cygni. The Crescent Nebula is right about here. Then down here is Alberio. Okay, Alberio is a very interesting star. It's a beautiful double. It's a K star and a B star combined. So you see orange and blue together in the same view. Really neat. Such a pretty star. And then right about here is the actual Dumbbell Nebula that we're looking at. All right.
Which is actually in Vulpecula.
Yeah.
The little fox.
The tiny foxy.
Just below Cygnus.
See the extra ring on the outside? See that? Let's do a color correction again and do a minor change. Not bad, man. This is something else, man. This will be brighter. So you can see the details now on the outside. I prefer to leave this down a little bit more so we can actually see details in the middle a little better. It allows us to see all this stuff. So we're going to save it under Dumbbell Nebula. All right. Oh, that's beautiful. Okay, that's 31 images. We're good with that. We're going to go back to our low light shot now, our low light sequence. We have time for one more object.
Let me guess.
Okay, you can guess.
Mr. Hitchcock.
Yeah. Okay, we can do that one.
You know, it really doesn't look like Alfred Hitchcock. The nose is all wrong. It reminds me of somebody, and I'm not sure who.
Bald guy?
Well, the nose is so different. I don't know. It rings a bell, but I can't say who. I've never seen the whatchamacallit movies by Rowling, but one of the bad guys in that, perhaps.
Okay. Okay, the Eastern Veil Nebula is where we're going to go. We've been driving toward it all night. So we're going to head there right now. Telescope's going to move just a little bit, not that far actually. And you'll see the veil as a faint arc coming in. There it is. Right there. And we'll center it up. We're going to move to the west a little bit. Okay. Oh, that Renee Cruz, that's interesting. Nice to see you, by the way. Okay, we're going to go to here. Maybe just a little lower. There we go. And a little bit to the west. There we go. All right, this exposure is going to be 20 seconds. And we're searching now for a guide star. I can say go because it won't take it if it's going to be oblong. But it's on its way. So we'll come out of low light mode and go into our deep sky mode. Here we go. And we'll clear this because it's up there now under Dumbbell Nebula. And this will be Vale East. Look at that. Look at that, guys. Wow. Right away, we're going to drop that out of the way. And we are going to get rid of the telescope for now. And just look at this. Wow. That is something else.
Let's see, who does that look like? Not Hitchcock. The nose is too pointy.
Yeah, I guess so. Oh, look at this. This is the eyelid right here. It looks like an eyelid. Lemony Snickets.
Got kind of an evil smirk on his lips, too.
And it's right like that, like, yeah. And he's got some food stuck on the outside, which is always gross. He's got that sloping forehead. That's pretty cool. Hello, Catherine Messick. Nice to see you. Isn't this beautiful, Catherine? This is the Vale East Nebula. It's the Eastern Vale.
When you showed me this last night, the one you took, pondering this, with the new camera and the shifting colors, the oxygen, given that the supernova explosion that produced the Vale Nebula is off screen to the right, I guess, or to the lower right, the gases we see here, that wavefront is pushing out from the right to the left, and the oxygen is ahead of the hydrogen.
Yep.
I think it's kind of safe to say. Maybe the hydrogen is catching up with the oxygen.
It's mingling here, that's for sure.
Yeah. So what does that say? Were those separate waves of gas? The oxygen came off first, and then the hydrogen. The oxygen because it was in the outer part of the star before it blew, and the hydrogen was in the middle, perhaps.
Well, this star was big enough to make hydrogen in its core. So,
make hydrogen.
Make oxygen in its core. So the progenitor star was clearly fusing helium into carbon, and carbon was going into nitrogen isotopes and then oxygen. So clearly it was making that. To go into a supernova, you have to be a star massive enough to make oxygen in its core.
Yeah.
And don't forget that a star of the size this one was probably dominated by the CNO cycle, which is the carbon, nitrogen, oxygen catalytic cycle that occurs. It's the only other way fusion can occur in the universe, actually. The previous way is the way the sun's doing it, and many stars like the sun. And that's the proton-proton process. I don't want to call it a chain because it's not really a chain, but it's a proton-proton process that makes hydrogen into helium in stars like the sun. More massive stars, they have this carbon to nitrogen to oxygen isotope process. So we get an inordinate amount of oxygen created in these stars as well. But look at these wisps. I want to show you a couple of wisps that I think were really remarkable. Okay, and that's down here. If you look down here, look at these details in here.
Yeah.
Now we're looking at something that is part of a light year across in these wisps. All right. This object and the other side of it and the rest of the nebulous detail in this particular supernova expanding remnant, as Daryl said correctly, it's expanding outward like this. So this left side, okay, here is actually expanding this way, okay, and way over here is the rest, okay. But you also have a central veil remnant. Now this, again, we're in a universe that is three-dimensional, so it's expanding toward us and away from us and in all directions around the star. The central veil is dimmer than the eastern, as this is, or the western veil on the other side, and that's because of this phenomena. When my hands are like this, you can see through my fingers. When my hands are like this, you can't, okay? And that means that we're seeing what looks like a higher density of gas because we're looking through this line of sight here, because it's really a curved expansion front that we're looking at. So as it gets toward the front, it's too wispy to see in many ways, but we can see it when we look at the central veil. But again, on the edge we see it, just like the western veil we see like that, and the eastern veil we see like this. So it's not just lines of stuff like this moving outward, okay? It's not lines of stuff like this. It's actually large spherical expansion front moving outward, and along the edges it just looks thicker because we're looking at more stuff through the edge, okay? So that's why it looks this way. That's why we see different filaments, and the way they're branched out depends on what they're encountering out in the interstellar medium. They could be striking other densities of dark nebulae, causing them to break into tendrils. There's also another potential that because this is a dense cloud of gas, but still highly rarefied, meaning only a few atoms per cubic centimeter, maybe, as I said, 30 as opposed to 3, okay, it's possible what's going on in here is related to a potential electrical discharge process where electricity is being sent through this cloud, and that could be responsible, for instance, for making tendrils like this. These types of linear formations like this could be electrically induced by electrical currents flowing through this cloud through the density of the gas, not in the vacuum areas but in the rarefied but still far denser than the space around it medium that makes up this cloud.
Now these materials this far from the supernova, they're not being illuminated into emission by the supernova, are they? Is this more of a shock front thing?
Yes.
Making them glow?
Yeah, their temperatures can be elevated up to millions of degrees by the interaction with the interstellar medium and being slamming in to other material. But keep in mind that the nebula is only about 1,500 light years away from us and about 8,000 years old. So there's a lot of distance from the central pulsar that was formed in this, and that pulsar is still hot. So it may, I'm not sure about the ionization distance for that pulsar, but it may very well be able to cause material to glow further out. I'd have to look at that, but the shock front is definitely happening, as Daryl said. So as this is moving out, it's striking other material, because it's not moving out into nothingness. The shape that you see here is entirely dependent on what it's striking as it goes out. It's like blowing smoke and seeing it be broken up by obstructions in its way. Same thing here. That's happening, but in very slow motion. you know.
I'm going to pull a mark on you. One more object.
Oh, you want to see the Western Veil?
Yeah, the Witch's Broom.
Yeah, that's a mark, all right. Okay, we'll do one more. Just one more. This is gorgeous. This is actually as beautiful as it was when I did the test for it last night. Just stunning. Let me bring back my telescope. Gesture in.
Jessica, who does it look like to you? Who is the evil guy in...
Oh, you're talking about Despicable Me and Gru?
No. J.K. Rowling's books.
Lord of the Rings? Is that what it was? Or The Hobbit?
J.K. Rowling. The whatchamacallums. I'm having a brain lock here. It's late.
Gollum?
J.K. Rowling.
Character from the book Gollum? My Precious? That thing?
That was J.R.R. Tolkien.
Oh, wow. That's right. What did I think?
Yeah.
Harry Potter.
Yes, Harry Potter. Catherine Voldemort. Does that look like Voldemort? I've only seen pictures of them. I've never seen the movies.
Wow, I gotta save this here.
They're not my cup of tea. Yes, thank you, Catherine and Eliza.
All right, so we're going to see one more object as requested by Dorelian Masoniki. That would be your
Darrell planet Krypton, if you please.
No, Dorelian. Come on, we're going to give you like a title, care of the Harry Potter franchise. Dorelian Masoniki. Okay, let's now...
Just don't call me late for dinner.
No, they might be having you for dinner. All right, we're going to go to this and see a star here. This is called 52 Cygni. It's a star that is a foreground star. It's not in... There's the entire Veil Nebula, as you can see. So somewhere in the middle here is where it all started 8,000 years ago.
I find it interesting that we don't see anything in the middle.
Yeah, there is something there, but it's just not visible. It looks like it could have gone to a black hole.
Donald Kunzer says the Joker.
Oh, well, I guess.
Maybe that's it.
Okay, there's 52 Cygni, and there is the Witch's Broom. We're going to move this over. I'm also running out of steam. It's 2:30 here, but that's okay. I said I was going to do this, and I haven't done it in a while, so heck, I'm sticking around. All right, so let's move over. This is the Western Veil. This is the other side of the supernova remnant. And I'm going to leave it about here because there's some stuff here that's really interesting to see as well. I'm just going to take us down just a little bit. Make sure that the very tip is in the process. I've never photographed this with this camera. This will be the very first time. So I'm so scared. Okay, gotta keep going. There's a little more. Okay, that's where I'm gonna stay. We may not catch the whole thing. I'm gonna go up one more jog here. We'll see some of the central veil over here. All right, that's where we're gonna stay. So now I'll do another 25-second shot. All right, and we're guiding already, so I'm going to go. We're going to get out of low light mode, go into deep sky mode. Entering deep sky. Here we go. And there's the last one we shot, the Eastern Veil on that side. That's stunning. That's up on our server right now for all of you to see. And so we'll clear it out now. And now you're going to see the other side, which is, as Daryl said, is called the Witch's Broom. Only because it looks like a witch's broom. Look at that. And there's the parts of the central veil. Right, so what we're going to do is we're going to hop out of this right now and allow us to see the full screen on this. I'll leave the telescope in the view for now. There's the very top. Look at the detail in here already. Again, first time I've looked at it with this camera. Wow. That is beautiful.
The upper part always reminds me of a rope tornado.
It does, doesn't it?
Just that the twisted filaments like that.
Yeah. In fact, it's the study of this side that has prompted researchers to suggest maybe electrical currents moving through these particles, which may be charged, is potentially part of the reason why we have these filaments as we do. Again, this star is a foreground star. It's not part of this in any way, shape, or form. But look at all this nebula here that you see. See, this is all the central veil, and then we have this on the edge. Let's zoom in on this. Okay, we have 3 images stacked, none ignored. Excellent. Look at this detail. This is detail that was not seen before and was elusive in our other camera. So again, if you're going to get a telescope and a camera, guys, talk to me first, or Daryl, and we can help you figure out the best camera for the telescope to get. All right, you want the best arc second per pixel rating that you can get, and we can help you figure that out. So if you want to take pictures through a telescope, we can let you know what the best way to do it is. Yeah, Stephen, many details and colors. Right, and as we zoom through here, let's kind of move through. Very, very nice.
Don't ask me about cameras. I know next to nothing about them.
That's true, huh? You don't really use cameras. Okay, ask me, I'll tell you. Go to SkyTourLive.org if you want to talk to me directly. My actual email is this right here. If you want to contact me, it's mufonanalyst@gmail.com. That's mufonanalyst@gmail.com. And that's on the stream now, so if you want to see it, you'll be able to see it. Okay. Let's go in here for a moment. And let's go to this. And let's reduce our noise, and it'll drop the color brightness a little bit, but we'll be able to see it a little bit more subtly, and we'll see more details in the filaments. Look at those. Those are such a tremendous tangle. You'll notice there's many parallel ones here. Parallel tangles of filament. All stuff that we could never see before. Moving over, you'll see now that we have this in here with this. It's really quite elaborate. This is oxygen 3, ionized oxygen, which is why we're seeing this color. The red is ionized hydrogen. And interestingly, we have this one region here, which looks white. Now, it goes all the way up to here, and that's fascinating. It's probably it's probably what's interesting about it is it's probably a shock front into dust potentially, and that dust is just reflecting some of the starlight that's nearby it, because it's being hit by it. Maybe it's a star like this or whatever. But what happens is, as this shock front moves out, stars get created along that shock front, And we see samples and examples of potentially of that because we see things like star trails, like trails of stars that follow certain paths within a nebula.
Is Pickering's triangle outside the field of view?
Oh yeah, Pickering's triangle would be part of this here. It's up here, I believe.
Yeah.
Now, if we were to then do a central shot, we could then mosaic all this. And we will, not tonight. I want to, but not tonight. Okay. Look at this, man.
Below 52 Cygni to the lower left, there's one very tight little blue filament, and it appears to have a star buried in it. Do you think that's real or just foreground?
This here?
Actually, a couple of stars. A little farther down.
This one.
That tendril right there, yeah. There's a bright star and a dimmer star above it. I mean, are those probably foreground?
Boy, oh boy, I don't know. I don't see any. Oh, this is beautiful. Holy cow! I don't see any immediate evidence for it being in this nebula, but it could be. I just don't see the immediate evidence of it.
Yeah.
There's nothing, in other words, to give it away. No deformed areas from stellar winds that you might expect to see.
Yeah, below the brighter of those stars, there's some interesting little details, little wisps and stuff farther down.
You mean
just
right here?
Right there, yes.
Mm-hmm. Again, all things we would never have been able to see before. So it's quite nice.
Well, thank you for humoring me. That's really cool.
No, I'm glad we did it, Daryl, even though I'm asleep right now.
Yeah, me too, pretty much.
So if we were to go into this, okay, this is 2,000%. We're seeing the color because we made it so, but most likely, with the camera, yeah, you wouldn't see any of this color if you were in this region. You know, and most likely, unless you were directly inside one of these regions here, you would not feel any impinging radiation on you to heat you up. This shock front is moving outward. As it moves outward along this front line, that's where you would feel the compression and thus heating. Okay, look at that. Now this, again, this is in 3D. So it looks like it's just 1, 2, 3 little segments. We might be seeing along a curve around the edge. It might be a curve around the edge here. So we're seeing 1, 2, 1, 2, 3 different curves that are actually look like this if you could see them from the other side. Isn't that cool? Wow. Okay, we're gonna go to 20 here. And I don't want to stop. This is just so beautiful, but I have to. I don't want to. Oh my gosh, guys. This is really a very successful sky tour with all of you. Look at this gorgeous tendril. We're going to zoom out now. Show everybody what the whole thing looks like. Okay. And I've got new settings in here, so I'm going to... Didn't mean to do that. I'll get rid of it. Fit the width. That's what I want to do. Okay. Where'd it go? Oh, hold on. I accidentally killed it, but luckily it didn't go anywhere. It's still there. So I can resume. And I'll save it Izabela West because I hadn't saved it yet. Alright, save exactly as seen. Alanis, how are you? I know it's beautiful, you're right, Catherine. It's just really stunning. You know, and it shows so much about the universe when you look at this. There's so much to learn by looking at this. This is why I love astronomy. This is why I had to get deep into astronomy. That's why I got my degree in it. I'm just very certain that people would appreciate learning how how we were born in the dark, in these dark nebulae, in the cold of space. Oh yeah, this is beautiful. Wow. I'm sorry I keep saying that over and over. I apologize. I should say sorry, not sorry, but I am because I keep saying it. Okay, let's save this guy right here. This is 24 images. That's quite a number for our stack. Looks good. And I shall now quit this for now. Okay. And we'll go into our low light mode again. Alright. Hoo-wee dee, that was a wonderful night. I hope you guys had a good time. Again, if you have just joined us for the first time, smash the like, as they always say. I'm an astronomer. I'm not a media guy, so you guys all have to help me with this stuff to make this popular. But do go to SkyTourLive.org right here. SkyTourLive.org, that's our portal. You can donate there. You can check us out. You can see what we do. It's an all-new redesigned site. And I hope you guys had a great time. I can see some wonderful comments coming in. Thank you. Daryl and I are very appreciative. So we'll see you guys the next clear night. And luckily I don't have to be up early tomorrow because I canceled the plumber who was coming at 8 o'clock tomorrow morning. Yeah, I just couldn't. No way. Not with a night like this coming. I had to forget that. Anyway, guys, you have a good night, and we will see you. Daryl and I will see you the next time around. And just remember, when you go out, look up, okay? Look up, but don't drive that way. Just look up when you go outside. The skies await. Good night, everybody.
You have a plumber coming on Sunday?
At 8 o'clock in the morning.
Holy cow.
No, I canceled them.
Oh, okay.
Yeah, I canceled them.
Thanks for coming, everybody. Hope you had a good time. Good night.
All right, everybody. So long.
Good night, ladies and gentlemen. Ray.
Okay. See, that was like, good night, ladies and gentlemen, and you too, Ray. It's like, was that pretty obvious, Ray? Daryl was having some fun with you. All right, everybody. Good night.
Good night.
See you later.